Okay, we're going to go through a series of videos here that work through this sample test right here. I want to go over the directions real quick for this because we want to make sure we do everything that it tells us to do. It says determine if the sequence diverges or converges. So I have to do that for each of these. This should probably be letter C. We want to show complete work and state that we're the test that we're using. Sometimes there's more than one test that'll work. So let's do the first one. This one should jump out to you as one that you know how to do. It is in the form sigma n equals 1 to infinity of 1 over n to the p. It's a p series. What's the p value? P is equal to 3. And the thing that we're looking for is either be bigger than 1 or smaller than or equal to 1. 3 is bigger than 1. If it's in the bigger than 1 category, then the series converges by p series. So that one's pretty quick, and it becomes the basis for a lot of the other things that we'll do later on. But let's go ahead on to letter B. So this is one for which there are actually two really good ways to show that it converges, which is what it does. It converges. And I'm going to go through one first, and then I'll talk about the other. So what I want you to see, and you might see this already, is that I could rewrite this as sigma n equals 1 to infinity of 3 times 1 over 4 to the n. That form should jump out to you. It's a geometric series. So I'll write geometric. And the next thing I want to do is identify the ratio. So when I write it like this, you get the ratio in this big parenthesis. The ratio here is 1/4. For every additional n value, we're going to multiply by 1/4 one more time. So I'm going to write geometric with, and then I'm going to write absolute value of r is equal to 1/4. It's a lot easier to write the absolute value. We've talked about that in class because then I don't have to write up a whole bunch of between -1 and 1. I'm just going to write less than 1. And when that ratio is less than 1, therefore, series converges. And that's all I got to say. If my 1/4 was, say, 5/4 bigger than 1, then it would diverge. But this one is less than 1, so it converges. I'm going to go ahead and do the other method. So let me switch colors. So you may say, well, how am I going to recognize that it's geometric? I didn't see that, right? Well, there is a test that we have that works really well in lots of scenarios. And I'm going to go ahead and do it right here. It's called the ratio test. So I can apply the ratio test. If I do the ratio test, I calculate a limit, and I either want it to be bigger than 1 or smaller than 1, and that'll tell me if the thing converges or diverges or converges. So I'm going to write L equals limit as n goes to infinity, absolute value, and what I'm going to write is a sub n plus 1 over a sub n. And then I'm going to go ahead, and I always like to write that line because that typically gives me points. So I'm going to write limit as n goes to infinity. And now I'm going to plug in those pieces. So I'm going to write 3 over 4 to the n plus 1 divided by 3 over 4 to the n. And then I'm going to copy dot flip. So what's that give me? The limit as n goes to infinity, absolute value. I copy the 3 over 4 to the n plus 1, and then I dot, and then I flip the next fraction, 4 to the n over 3. And then that is equal to, watch, the 3's divide out. This 4 divides with all but the last 4, so I wind up getting 1/4. You should see that. That's good. This is a pretty quick ratio test one. And then what I want it to be, I want to indicate that that is less than 1. And then I wanted to say, therefore, converges by ratio test. And that's all the work I have to show. You can do either the work in green or you could do the work in purple. Both would be good and sufficient to show that this thing converges. All right, on to the next one. I'm going to go back to green, I think, for this. Yep. So part C here. What you should recognize is that this is an alternating series. What that means is that this -1 to the n makes it so that this series alternates positive 1, negative 1, positive 1, negative 1, positive 1, negative 1. So once you recognize that it's alternating series, we can say the series alternates. And then I just have to calculate a quick limit. The limit as n goes to infinity of n over n squared plus 4. Where did I get that? What I do is I just take what's left over after we get rid of the alternating piece. So I look at the terms without the negative 1 to the n. And you should see that in the top I've got a polynomial, an n polynomial, and at the bottom I've got an n squared. The language that I like to use is that the n squared beats the n. So what we wind up getting is something that's like a 1 over infinity, or something where the infinity in the bottom grows bigger. You could also hop this. You could use Hopital's rule, but it's unnecessary. When I get an infinity in the bottom that's bigger than the infinity and that's hopped like this, we get that the limit is 0. It's also good to say a sub n plus 1 is less than a sub n. And then after that, we can just say, therefore, those are the conditions of the alternating series test. So we can then after that say, therefore, converges by AST, alternating series test. And that's C. We're good to go. Let's jump on to D. Okay, D here. So what I want you to see here is that we've got an n squared in the top and then a 4 to the n in the bottom. You should have enough experience with this that this should jump out to you as like, well, LCT, limit comparison, is not going to work. It's not a p-series. It's not geometric like this one because I got an n squared instead of a 3. So we use the test that I sort of suggest to try most often, which is the ratio test, which is what I did up in here in purple for the previous, for this one up there. And this one, like ratio test, is the one you want to use. So I'm going to write the limit as n goes to infinity. I always write absolute value a sub n plus 1 over a sub n. And then I'll make a little barrier here. That is equal to the limit as n goes to infinity, absolute value. I'm going to write n plus 1 squared over 4 to the n plus 1. And I'm going to divide it by n squared over 4 to the n. That's a sub n plus 1 over a sub n. And then I'll come down here. That gives me the limit as n goes to infinity, absolute value. I'm going to do a little bit more work on this one than I did on the previous one. Show a little bit more in-depth steps. It's the limit as n goes to infinity of, I'm going to copy dot flip, should be a plus 1, n plus 1 squared over 4 to the n plus 1. Dotted with, all right, now we'll flip it. I get 4 to the n, 4 to the n over n squared. You might see how this cancels out, and you might be able to do this in its current form, but I'm going to go ahead and reorder it in a way that groups the like terms together so that they're easier to see what cancels. This is the limit as n goes to infinity, absolute value. I'm going to write n plus 1 squared over n squared times 4 to the n over 4 to the n plus 1. Now, what cancels here? Well, in this term that I wrote, the 4's, all of the 4's in the top cancel with all but one of the 4's in the bottom. So I'm going to write equals limit as n goes to infinity of the absolute value. And then I'll write 1 over 4 for that piece. And then I need to figure out what this limit evaluates to. So in this one, I've got an n squared polynomial in the top, because if I were to FOIL that out, I would get an n squared. And I've got an n squared polynomial in the bottom. And they cancel out and give me just 1. I'll go ahead, and write that. But I'm going to give another explanation as to why this works like that, why we get 1. Well, on the bottom, I'm going to get an infinity squared. And then at the top, I'm going to get an infinity plus 1 more squared. That plus 1 is not going to make a difference. I've still got an infinity squared over infinity squared. So when I divide them out, or you could say, let's ignore this thing right here, because it doesn't matter as n goes to infinity, I got an n squared over an n squared. They wind up canceling each other out. So hopefully all those logics make sense. And then look at this. There's no more n's in this. So what is it? It's just 1 times 1/4, which is 1 over 4. Remember, I'm always looking for this to be less than 1 or bigger than 1. So I just write less than 1, and then I write therefore converges by the ratio test. Hopefully that helps with these. I will hopefully make another video on the other two, and hopefully they should be helpful. See ya.